So now with the other side of the unit here, a combination is often simpler than a permutation. A combination is basically a selection of a set of objects in which the order is not important and the objects are not going to be arranged. So you have a set of objects and you just want to see how many ways you can select from them. But the order in which you select is not important. Much like permutations, just like permutations have certain clue words like arrangement and order, one of the main clue words for a combination is select, right? To select or a selection of. In other times, though, if it doesn't seem like order is important, then you know you're dealing with a combination. And of course, the R pertains to the number that we're choosing from the set. So we're going to write here number chosen from set, and that's really the same thing as it was in the permutation formula. A group of 15 people, 9 females, 6 males, perform a subcommittee of 7 people. How many combinations are there with 7 females, or exactly 7 females, and then be at least 4 females? So these are two different types of combination problems. We're going to approach each separately and thoroughly. So the first problem reads, a group of 15 people, 9 females and 6 males, form a committee of 7 people. So here, I'm going to underline that word form because that's another word that kind of indicates a combination, because you're basically selecting, right? So, and it doesn't really matter how you do that. And that's in particular what makes this question a combination question. So, how many combinations are there with 7 females exactly, and then at least 4 males? So we're going to solve this one. Both of these are two different combination questions. So the first one is pretty straightforward. From the set of 9 females, because you want females only, you're going to choose 7. So from 9 females, you're choosing 7, and that's going to give us 36 possible combinations. Now, if I want to see how the formula looks like, or how these numbers would apply to the formula, well, remember that the formula is n factorial over r factorial times n minus r factorial. And so subbing in the numbers would be n factorial over r factorial, which is 7, and then n minus 7 factorial. You plug this in, and you're also going to get about 36 combinations. So this is a relatively straightforward question. Again, whatever we're seeing formed or select, we know that these are combinations. Now, much like we saw with the permutations, you could also have combinations with multiple cases. And just like in permutations, some of the key words that indicate that would be and, or, at least. So in this case, we want at least 4 females. So we know, and I'm underlining this here, and I'm writing multiple case. Now, what that means is, because you're selecting 7 females. So if it's at least 4 females, that means that for one combination, you have 4 females and then 3 males, right? Because, again, you have to make 7. We're choosing 7. Then another combination, you would have 5 females, because it's at least 4 females. So that's 4 females and above. At least 5 females plus 2 males. Then we would have, as another combination, 6 females plus 1 male. And I'm just rewriting that 1 here. And then, of course, we could have 7 females all together here. Now, each of these has to be written as its own combination with its own combination formulas. Now, another thing that I want to point out is when it says at least, that leaves room for the word or. And so we say 4 females plus 3 males, or 5 females plus 2 males, or 6 females plus 1 male, or finally 7 females. So or in math usually alludes to an addition sign. And then the word and alludes to multiplication. So now what we're going to do is we're going to solve each one of these one by one. Okay, what I've also done here is those pluses, I've actually wrote the word and I did that because, we're working with the context that and signifies a multiplication. So for the first combination, right, you got 4 females, so it'll be 4, I should say, out of 7 or 9 females, you're going to choose 4. And then that's going to be multiplied by out of 6 males, you're choosing 3. Okay? And then plus or out of 9 females, you're choosing 5. And multiplied by out of 6 males, you're choosing 2. And then plus or out of 9 females, we're choosing 6, multiplied by, because it's and 1 male, out of 6 males, we're choosing 1. And then finally, multiplied by, or I should say added to, not multiply because it's or, just 7 females, which is out of 9 females, we're choosing 7. And so you get the value of each of these, and then you're going to add them all up, and that is going to be the final amount of combination. And that gives us a total number of combinations of 4,950. And what I've done here over in pink, which I'm underlining here, is that's just the total of each combination. So the 9 choose 4 times 6 choose 3, that gives us 2,520. But the full number is this, 4,950 combinations. A committee of 5 people is going to be selected, and that word I'm going to underline because that tells us that this is a combination, because the order doesn't matter when you're just randomly selecting to form a group. Form a group which contains 8 men and 7 women. How many committees are possible with A, no restrictions, B, no men, and then C, at least 1 man? So for A, if there's no restrictions at all, and you can select any 5, no matter whether they're men or women, from the 15, well, then we would just say from the 15, we're choosing 5. Now in the formula, it would be 15 factorial divided by 5 factorial multiplied by 15 minus 5 factorial. And this is going to give us a total of 3,003 possible combinations. Okay, and that's the same thing if you just put it into your calculator as well. But we showed the formula just so you can get used to the expanded version in case we ask you to isolate for a variable. Now for B, and I'll extend the line over here. For B, what if there were no men? Okay, so that means that it's only women that are going to be selected in this committee of 5. So out of 7 women, we're going to choose 5. And they can be in any order or no order for that matter. So this is a combination. So if you go 7, choose 5, that is going to give us a total of 21 possible combinations. Now, again, formula-wise, that would be 7 factorial divided by 5 factorial multiplied by 7 minus 5 factorial. And again, that's the expanded version. So I solved the first two. I got 3,003 combinations for the first one, and then 21 combinations for the second one. Now for C, if there was at least 1 man. So now this tells us, the at least part tells us that it's multiple. There are multiple cases that are possible for this combination. So now we have at least 1 man. So that could be 1 man and 4 women. Okay, and so that would, since it's and, that would be a multiplication. It could also be 2 men and 3 women. And we can make this go all the way to 5 men only. Now, this would take a really, really long time. So one possible shortcut for this problem would be that if we write at least 1 man, then this is the opposite, right, of no men, which we asked for in B. So it's the opposite of no men, because now we want at least one man per combination, and that leaves us room with up to just men in the combination. So if this is the opposite of no men, then we can essentially just do the 15 combination 5 subtracted by the combination where there is no men. And the difference is going to be all the types of possible combinations where men are allowed in the combination. So in this case, that would be 3003 minus 21. And then that would be 2,982 possible combinations. Now, you could do this full thing if you're more comfortable, again, just doing each combination separately and then adding them all up. That is totally fine. It would just take a long time. This is another way to think about it. And it's a lot more efficient way of doing it too, and you get the same answer. Now, a lot of students get a bit overwhelmed when it comes to decks of cards, combination and permutation questions. And that's because there seems to be a lot going on. So what we'll do is we'll spell out how a deck of cards works first here, and then apply this to a couple of problems. So remember that there are 52 cards in total in a deck, in a standard deck of cards. There are 4 suits. So we're talking about the symbols that are often accompanied by a number on the card. So that would break down into hearts, diamonds, spades, and clubs. And then for each of those suits, there's 13 cards. So you have 13 cards that are under the hearts suit and 13 cards under the diamonds, spades, clubs, etc. So using a standard deck of 52 cards, how many different 5-card hands are possible with no restrictions? So if there's no restrictions, well, the formula is quite easy. Out of 52 cards, we can choose any 5. And so when we plug that in to your calculator, this would give us an answer of 2,598,960 possible hands. Now, what if we wanted to make a 5-card hand that has exactly 2 kings? How many combinations would that allow? Well, remember that there are 4 different suits and each one of them has a king. So from the 4, we're going to choose exactly 2. But remember, we have to make a 5-card hand. So then once we've chosen from the 4, we want 2 kings and 3 other cards. So then out of the 48 cards that remain, we're going to choose 3. And so we plug in this combination, we do it in our calculator, and then we get about 103,776 possible hands.